Hello, I'm Colin Usher, Senior Research Scientist at Georgia Tech Research Institute, coming to you with a full head of quarantine hair. I will be presenting on mitigating disease and reducing potential for cross-contamination in commercial poultry flocks using robotics. Without further ado, let's get started. We are living in unprecedented times. Do I even need to say anything about the virus that is running rampant throughout the world? But just to remind us that COVID-19 isn't the only thing out there, a highly pathogenic avian flu, H7N3, was detected in a turkey flock in April in the United States. One industry in particular has benefited from the current situation. COVID-19 has greatly sped up the growth of robotics. Even before the pandemics, robots were on the rise, and the market for service robots was growing. For example, in 2018, 271,000 service robots were shipped. That's an increase of over 60% from 2017. As new information is learned about the spread of COVID, there comes a demand for robots to take over tasks from humans in high-risk areas. This includes robots doing tasks such as disinfection. If you look in the upper left-hand corner, you see a picture of a robot with UVC lights mounted on it disinfecting a hospital room. This company has sold thousands of robots all around the world. In China, in particular, more than 2,000 hospitals will be using these robots in every province. Other robots carry out utilitarian tasks such as taking temperatures of sick patients or delivering food to them in their rooms, allowing the workers to stay out of harm's way. They also allow interaction such as teleconferencing with family and even doctors. And finally, in China and New York City, they are flying drones with speakers on them yelling at people, "Hey, put your mask on!" So you may be asking yourself, how can robots be used to mitigate disease in flocks? Well, the premise is actually pretty simple. The idea here is that the more tasks that a robot can do in a house, the less a person needs to enter. It's well known that the greatest vector for disease and contamination in a house is the workers entering the farms from outside, and even going into one house that might be contaminated and then taking that contamination to other houses on the same farm. If you can keep people out of the houses, then you can mitigate or reduce the potential for contamination in those houses. You may also be saying to yourself, robots? I don't know. But in reality, there are several robots already available. Here are but 4 examples. In the top left, you see the T-Bot robot, which drives around on the floors in chicken houses and encourages movement. In the top right, you see a disinfecting robot from Octopus Robotics. This robot also runs up and down the houses and can aerate the litter and spray a disinfecting mist. In the bottom left, you see a robot that assists in management activities in Chinese facilities. These houses can have up to 100,000 birds and are managed by one human. This robot roams up and down the aisles looking for mortality and malfunctioning equipment and can report that information back to the farm hands and managers. In the bottom right, you see the Chicken Boy. This is a gantry-mounted robot that also roams through the houses and is able to identify mortality and even identify some diseases. In order to achieve our goal of reducing or eliminating the need for farmers or farmhands to enter the houses, we believe these robot systems need to do more than just sense. We believe they also need to be able to manipulate the environment. To that end, we have developed a robust robotic solution that is able to navigate the houses autonomously, interact with the chickens, execute searches. It also has the ability to do environmental sensing. It can do microclimate mapping, autonomously identify chickens, equipment, and eggs using special artificial intelligence routines. And finally, it can do some manipulation. As you see in the picture here on the right, this is a robot arm on the front bumper of the robot that is able to pick up eggs. This capability has been tested and demonstrated in test commercial houses. We are also currently working on mortality removal with a custom developed arm and algorithms. Here you can see 2 videos showing examples of the robot autonomously navigating a broiler flock. the top video was taken during week 1 and the bottom video was taken during the 5th week. On the left-hand side, you see a diagram showing the executed plan for the robot. Essentially, the robot is assigned waypoints in the house that it will drive between. These waypoints can be at the corners or on opposite ends of the house. The robot will then autonomously drive to these waypoints. While it is driving, it is dynamically sensing the location of the chickens and equipment around it. If a chicken is in the way, you will see the robot slow down to a stop and then gently nudge the chickens to encourage them to move out of the way. If the chickens do not move, the robot will turn and repan a path to move around them. During this whole time, it's also searching for eggs. If it sees one, it will go into an egg pick mode that we'll talk about later. I previously mentioned the sensing capabilities of the robot. Here I will go into a little more detail. In the top left image, you see one of our sensing suites cobbled together that allows sensing of temperature, light levels, humidity, several different gases, and we even threw a Geiger counter in there for the fun of it. This allows the robot to autonomously map the microclimate environment down to a resolution of 2 inches as it traverses the houses. There are also several vision-based sensors, both 2D and 3D, on the robot that allow for machine learning, classification, and segmentation. Artificial intelligence algorithms have been designed to allow for detection of chickens, eggs, and equipment in the house. In addition, the 3D sensors allow for localization of these objects once they have been identified, and this is critical when it comes to tasks for manipulation, as you will see shortly. You can see here in the images in the top an output from the neural network identifying both eggs and chickens. In the bottom, you see a montage of video from a 2D and 3D camera sensor that is synchronized, so as you see the robot moving around, you can see both the chicken in 2D and 3D. With the completion of the autonomous navigation and sensing routines, we naturally moved on to look at manipulation. The first task we picked was egg picking. We started this by acquiring a commercially available robot arm you can see in the upper right hand corner image. We attached a camera to the front of it and developed visual servoing routines that allow the robot to drive to and pick up eggs. If you watch the video in the bottom here, you can see the robot autonomously navigating the floor, searching for eggs. Once an egg is identified, the robot will, via the 2D and 3D sensors, localize that egg and drive up to it. Once it has approached it, it will extract the arm. If the arm cannot reach it directly, it will actually command the robot base to make fine corrections, as you can see in this video. And then finally, it will align itself, approach, and pick the egg, placing it in a temporary holder on the robot until it can take it to a drop-off location. In all of the previous slides, I have summarized things that the robot can do autonomously, but automated things are not the only stuff that the robot can do. And in fact, farmers might just want to go into the house and see what's going on or take a look at things. But instead of having to physically go to the house and enter it, they could instead just dial into the robot and take over teleop control. You can see a demonstration of a 360-degree sensor on the robot in the video playing in the top right. While this is a still image, we actually can run this in live and operate the robot using both virtual reality goggles or a tablet or a laptop or a PC, even a cell phone. You can drive the robot anywhere you want, and you can look around the robot in any direction. We think this is powerful because it allows farmers to then go and get a quick status of their flock without having to physically enter the house. coming back full circle to talk about how the capabilities of the robot we just discussed might be used to reduce the potential for the spread of disease or cross-contamination, we enlisted the help of some students in the MBA program at Georgia Tech to assist us in establishing the value of the robot that we have developed. They estimated that the robot could reduce staffing requirements by 50% if it simply could do floor, egg, and mortality removal. Additional benefits from monitoring can be carried out remotely, leading to even further reduction of the need of personnel entering these houses. As mentioned before, it's pretty well known that the primary vector of disease coming into these houses is the people going in and out of them. So if we can reduce people coming in and out, we can reduce the potential for the disease and contamination. I would like to briefly make a couple of acknowledgments. First and foremost, to the Agricultural Technology Research Program, the funding apparatus out of the state of Georgia that enabled this work. Both Georgia Tech and the University of Georgia, even though we might be rivals in football, we work very closely together, and without them, there's no way this project would have been successful. I would also like to thank several industry partners that have also allowed us to test in their facilities and provided great input. And finally, I would like to thank all of the students that have worked on this project, for without them, it also would not have come together as it has. With that, the presentation is concluded. I would like to thank you for listening, and I have attached my contact information to this slide, so if you have any questions beyond this conference, please feel free to reach out and contact me. Thank you very much.